Interesting thing. Okay, so now that we're recording, here's the data showing sunspots. Now, if you look there, what does the top one look like?
Looks like tire tread.
Okay, tire tread. Most people say butterfly, so it's called a butterfly diagram.
Oh yeah, I clearly see it now.
I mean, I guess now that I know.
Now, if you look, yeah, there's lots of things you could see, right? Like, it does look a lot like a motorcycle tread, for instance. You look at these and you see they're not uniform. They're not always the same, but you definitely have a repeating cycle. This cycle repeats about every 11 years. And on the bottom line, or bottom graph, we have just the number of sunspots on the sun at any given time. And you see the number of sunspots goes through a similar cyclical pattern. And where do we have the most sunspots? Well, let's just take this here. The most sunspots is right in this ballpark. And so it's early on in that butterfly cycle is when we have the most sunspots. And then it goes down. I just chose one which happened to be the one you chose because it was the highest, I think. I was meaning where in the cycle, not what years. So this is what we have for what's going on with the solar cycle just by looking at sunspots. And then we want to figure out what's going on. And the best understanding we have of what's going on is called the Babcock model. And the Babcock model says, well, we know that the sun has a differential rotation. The rate at which the sun rotates is different at the pole as compared to the equator. Now, being on Earth, that seems odd because the Earth is a rigid object. Everything rotates at the same rate. But for something that is a fluid, like the sun or Jupiter or Saturn, you don't have to have everything rotate at the same rate. And so you can see here from this graphic that Saturn has the pole is about 26 minutes shorter for its period. So if you were up near the pole of Saturn, the time it takes to do one rotation would be about 26 minutes less than if you were at the equator. Jupiter, it's also shorter, but a smaller amount, only 5 minutes shorter. The sun is the flip of that. The sun has an equatorial period of 25.05 days, but the polar period is more than 10 days longer, 34.3 days. So the sun has material orbiting faster at the equator. Now we have magnetic fields in the sun, make magnetic field lines, and those magnetic field lines basically are making loops that go like this. But because you have the material that's close to the equator rotating faster than the material that's close to the poles, those magnetic field lines start to get deformed because of the differential rotation. So when this slide comes up, here we see some magnetic field lines and how they get deformed, we believe, by that rotation. And after a while, they get all tangled up. And when they get all tangled up, the interaction between magnetic fields causes some magnetic field lines to come up out of the surface and go back in. That was green on green. Not our best choice. Oh, really? I didn't even realize I could back up to go to a preceding slide.
What?
I hit the undo button and it took me back to the previous slide when I did undo one too many times. It undid, in other words, the page forward.
That's really interesting.
Yes, it's curious. So the magnetic field lines come up, go out, and come back in. Now, do you remember what we call these things up here?
They're the flux.
Starts with the P. Yes. So the prominence there is material that's coming out of the sun flowing along the magnetic field lines that were making the sunspot and going back in. Now, of course, how do we know that this is magnetic in nature, these sunspots? Not by guesswork. It's something that's measurable. We have the Zeeman effect that tells us that when we have certain absorption or emission lines, if you put in a magnetic field, they will split and make, my example here is making a triplet And so I have a magnetic field only in this region. And the amount of that split actually tells me the strength of the magnetic field. So by looking at the absorption spectra in the sunspots, we see that splitting. We know how to interpret that. We can do this in the lab on Earth, and we can actually measure the strength of the magnetic field there. And so from those measurements, we know that the magnetic field is suddenly very strong here compared to what it was outside of the sunspots. Now that strong magnetic field tells us further what's going on with a sunspot. That strong magnetic field inhibits the convective flow upward. And so basically the heat gets blocked. Yes, it says hot rising gas blocked where I put my arrows. So that hot rising gas gets blocked because of the strong magnetic fields. And so the surfaces there get cooler because the hot material can't rise up to keep heating it. And so these sunspots are cooler. What kind of temperature is a sunspot? You should know this at this point.
Really hot.
Okay, really hot's true. Cooler's true.
Like, 4, those okay.
They're in the ballpark of 4,000 kelvins.
I said 3,000 kelvins.
Okay, they're in the ballpark of 4,000 kelvins. What's the temperature of the rest of the sun around it?
5,800.
Okay, 5,800 kelvins. Now, that would suggest that where you have sunspots, you have less radiation coming off because the radiation is proportional to temperature to the fourth power. But experimentation shows that while you do get less radiation from the sunspot itself, the material around it gets hotter because of all of the deflected convective currents, and you actually have more radiation that comes from the sun when you have a sunspot because of the higher radiation around the sunspot. So sunspots correlate to the sun giving off more radiation. Question or no?
Is that okay? That makes sense.
Okay, so first clicker question. How do we know that sunspots are magnetic?
Because
Bible does not talk about this.
how interesting would that be if the Bible talked about some weird astronomical thing? We just
It
had
does. Does that mean we can see the magnetic field?
Do you have your stuff?
Yep.
I have a question.
Yeah?
We can see the magnetic field like through instruments or through like visually see them?
Visually, like your eye can see it. Okay. 1, 1, 3, 7. And the answer was, moving on without much discussion, it's that Zeeman splitting, the Zeeman effect. Right? We can't see magnetic fields. If we could see magnetic fields, you'd take the kitchen magnet and be able to see something coming off it that relates to it. The lower temperatures don't mean higher magnetic fields. You have a lower temperature because of the strong magnetic fields, but you can have other reasons for low temperatures. And, well, magnetic fields are believed to be the reason that the corona is so hot because of interaction. So we can't have magnetic heating, but C was also incorrect. Okay, I think it's another clicker question. Come on. Nope, not. Going to talk about global warming first. Now, this is a very politically charged topic. The two graphs on the right are from your textbook. The one down below shows us looking at sunspot activity as long as it's been recorded. And you notice that it's very distinct there from just a little bit before 1650 out to a little after 1700. You have a region with virtually no sunspots. What did I tell you happens to the amount of light coming off of the sun, the luminosity, when you have a sunspot? It increases. So here when we don't have sunspots, what's happening to the sun's luminosity? goes down. Now the sun is our source of energy. The sun was not exaggerating when we said we need its light, we need its heat, we need its energy. The sun is over 99% of the Earth's energy budget. So if the sun stopped shining, we would just freeze. That's the end. Possible.
The end.
So here where the sun gets just a little lower, I mean, it's still hot. It's still giving off a lot of radiation, but it drops by a few percent, and that's enough to make a big difference. So during this Maunder minimum, global temperatures started dropping. And so we had things like the River Thames froze solid, and they would have ice skating parties out there. You know, look at Cape Big Bend Parliament out there in the Thames. In front of that, it'd be ice skating on the river. Not something you do these days because it's too warm. Not something you could do before that because it was too warm. But they had global cooling because of this Maunder minimum. Now, if you look at the current trend, you probably see a trend. A downward trend, right? I exaggerated a little bit because I wasn't very careful. But there's a downward trend in the solar activity. Now, what's happened to temperatures on Earth? And we can see during this period, we should have had an increase in temperatures, right? Going from 1900 to around 1950, it was definitely having more solar radiation. You'd expect the temperatures to go up. Since the radiation started going down, what's happened to the temperatures?
Well, they continue going up.
If you look at the cyan line on this upper graph,
Oh, is that how you pronounce that? I've been pronouncing it cayenne this entire time. Dang it, English.
yes, the pepper line, as we like to call it. Okay,
It always boggles me.
it shows it shooting up here. Now, of course, keep in mind, when do we have the hottest temperatures on Earth?
There are no sunspots
No, I mean cyclical, yearly cycle.
at the end of the 11 years.
We tend to have it not on the summer solstice, but later on.
Yeah.
The summer solstice is when we are getting the absolute most solar heating. But that's not the hottest day. Why not?
Because the Earth is on like getting hotter and getting hotter. It's on an upward swing.
Yeah. We haven't reached equilibrium yet. And so we're still warming up. And even though the sun is not giving off as much heat in July, the temperatures are still rising in July because the sun is still giving off more heat than we're giving, or we're receiving more from the sun than we're giving off. So up here, even though the sun has stopped heating up, it's certainly conceivable that it was still giving off more than we were, as we're receiving more radiation from the sun than we're giving off, and the temperature would go up. But if this downward trend continues, you get down to somewhere around, let's say this, okay, let's change back to the drawing tool. Get down to somewhere like the average here, which it was just about to hit when this graph ended. You would hope that the temperature should at least flatten out and maybe start to drop, right? Now, if you look at their graph, it would make you think, au contraire. So I put another graph, which we'll see a little more carefully on this next slide. This is a graph of the same data, but the graph goes on longer in time. Now, you might wonder, what's this fuzzy thing, the gray? That's the uncertainty in temperature. They were very uncertain in their measurements until somewhere around 1950. If you look here, going back to, on the line tool, we had a general increase in the ocean temperatures corresponding with what we saw in the preceding graph. But what's happened since around 2000? Okay, that's too low, but it's been pretty much a flat line since around 2000, which was conveniently where they left off here pretty much, right? This line here cuts off before the other. Well, I'm doing a really good job of straight. Okay, I have actually the straight line tool. Let me, dashed line is going to. So there's where they appear to have cut the data off. And it doesn't actually match because at the point they cut it off, it should have driven down. Not sure why it didn't drive down like this does. So temperatures have been roughly constant for the last 15, 16 years. But of course, it's not cooling, right? It's not been getting cooler, and they're having cool things like there was a tornado 13 miles from my parents' home in California. Was it yesterday or the day before?
Where does it happen?
In Modesto, California. Yeah, those used to not happen. Well, Milankovitch had proposed back in, the 1800s, that the weather cycles on Earth were dominated by, well, he said 3 factors, but there's a 4th one you have to include. The eccentricity of the Earth's orbit, the obliquity or tilt of the Earth, and the precession. Now, I spent a lot of time on this. I am not going to get anywhere close. I was hoping to go through like 30 slides today. I'm on, 7? Anyway, the eccentricity, that's how close to circular our orbit is. The more circular the orbit is, the more uniform the seasons are. The more eccentric, the more out of whack they are. The eccentricity of the Earth's orbit has about a 100,000 year cycle, going between 0.0005, very, very circular, to 0.0607. Right now we're at 0.017, which is on the more circular side. The obliquity is the tilt. Right now we're 23.5 degrees tilted. We've talked all about that and how it relates to the tropics and the Arctic and Antarctic. But that tilt actually goes through a cyclical period of about 40,000 years where it goes between about 22.1 degrees and 24.5 degrees. What happens when we're more tilted?
Well, it depends on where we're more tilted towards.
Well, as far as seasons, the seasons become more extreme. So the more tilted you are, the more extreme. And finally, precession. As we go around the sun, our north pole is actually precessing like a top rotates around, so that approximately, 11 or 13,000 years ago, Vega was as close to the north as you had any star. So Vega would have been considered the North Star 13,000 years ago. Right now it's Polaris. Get another 13,000 years, it'd be back to Vega. So we have a 26,000 year cycle. And then the last one is the solar activity, the sun's activity. All of those things go together to predict the temperatures, we believe, according to Milankovitch. So experiments have been done to try to match the temperatures predicted by Milankovitch with the actual temperatures. And there's a very strong match historically. But that match appears to diverge in the last 30 or 40 years, suggesting that maybe man now is becoming a significant factor and wasn't before. Come on. Sunspot cycle 24. That's the one we're in now. This is the most recent data as of last week. And what do you see going on? It's coming down. The number of sunspots in this cycle is like half the number of sunspots in the last cycle. There's also an extension of the time. The sunspot cycle is about 11 years per repeating, but the time is starting to stretch out, it appears, as well. What do these things mean? The truth is we don't know. We think, we being the scientists who study this, that this indicates that we might be going into another solar minimum. Nobody knows what causes a solar minimum or what's going on to make a solar minimum. But these suggest, based on other measurements, that we must be going to a solar minimum. If we're going to solar minimum, what does that tell you about the radiation the sun's going to be giving off over the next 30, 50, 100 years?
Solar minimum.
That's where you don't have many sunspots at all. The sun is just a hot rock without sunspots on it. Not rock.
Is that a bad thing?
Plasma ball.
Yeah, plasma ball.
Is that a bad thing?
I didn't hear you.
Is that a bad thing, not having the sunspots?
Is it a bad thing? Well, what it means, since no one's actually answered what I'm looking for, it means
it'll be cooler.
It'll be cooler. It's going to be, well, yeah, cooler, giving off less radiation, heating the earth less. if that happens, what should happen here on Earth?
We should also pray time start to go down.
It should start to get a little cooler. So, if nature rather than man is responsible for global climate change, what should we expect to happen to global temperatures in the next 30 years? I like this because it gives us some kind of measurement where we can start saying, hey, is it us or is it not us? Because all of the models the scientists put together that says, it's humans, say one thing, and this says Seth and Labored? Holly?
I just have a question. So it seems like it's been getting warmer. Like we had snow here at this time last year, and then like other places where I'm from too. It just seems to be, getting warmer.
Okay. There are a lot of things that are confusing about climate versus your local weather. When we have the global climate change, some places may get warmer, some may get cooler. And so taking single points of data, like saying the city of Lincoln had this, isn't all that telling. You have to look at the global picture. So whether, some people will say, we had the hottest day on record. Others will say, we had the coldest day on record. They'll both use it to make opposite claims. And both of them are using it wrong. You have to look at the global data. Now, the global data that I showed you ocean temperature, surface temperatures in the ocean, because that's what the textbook used. That's not the only indicator for for warming and climate change. Other indicators are the temperature in the upper atmosphere. Temperatures measured at land-based measuring stations, like at the Lincoln Airport. Now, a lot of these have difficulties you have to work with. If you're taking a measurement at the Lincoln Airport, something you may not know about is that when people move in, the temperature changes. And so as the population of the city changes, the temperature naturally changes regardless of what is happening globally. And so the people who are working on climate try to take that into account. So they say, okay, here's the temperature on this station, and we're going to adjust it hotter by this amount because more people have moved here. And so, of course, the people who are pro-global warming say, yes, that's what you have to do. And the people who are, I say pro-global warming, I need to be clear. The people who say man has caused global warming say, yeah, that's what you got to do. The people say, no, global warming is a phenomenon of nature, say, okay, so you have a model that says, let's push these temperatures up, and they go and analyze them, and they find lots of places where they say, you didn't do that right. It's a difficulty that has to be faced one way or another. And am I here to say which way is the right way? I don't know. Another thing to keep in mind, we talk about the ice caps. What's important about an ice cap? They have a lot of water that is frozen.
And completely inaccessible.
And, yes, completely inaccessible. But in terms of temperature, if the Earth receives more energy than it gives off, generally you say, well, that's warming. But what's really going to happen is the ice melts until the ice is gone. Then when the ice is gone, then the temperature really starts taking off. And so if the ice pack is getting less and less, that's a sign of global warming. If the ice pack is getting more and more, well, that would be the opposite. Ice pack also plays a big role in this whole debate because if you have more ice, the ice reflects the solar radiation, you have less that stays in the Earth. Okay, we only got 3 minutes left. I feel in astronomy class it's important to have some understanding about what's going on. We've talked about the greenhouse effect. Now we talk about the Milankovitch hypothesis and the things that should be heating up the Earth. And something that by the time you're my age, you can point to your kids and say, back then we thought this, and now we know because. Actually, I don't think my voice is like that. You can argue with me if you feel you need to. Okay, yeah, I'm going to stop there. I mean, we only have 1 minute, and It's no point starting a whole new section with 1 minute.
Are we going to do a review tomorrow night?
Yeah, we'll do a review. There'll probably be some new stuff on that review too. Yeah, the weather report says we won't be able to go out tomorrow night. We'll see. If it's clear, we'll go out, of course.
It depends on global warming.
I don't care with both.
You had a question, Holly?
So then after Thanksgiving, there's only 1 week that we can do it before we have to do it on the paper?
Well, yeah, if it's clear either of those weeks, you can do either of those weeks. Right? If it's not clear the second one, then you'll have to do it on paper. But you can also arrange, Reese has done, I think, half the class. A lot of people he's done outside of the regular lab.
Haven't done it yet.